Hey everybody, welcome to this next video lesson. And in this video lesson, I'm going to show you how you can use density as one of our conversion factors in a process of stoichiometry. Now, do you remember this picture that I drew on the last time we talked about stoichiometry and the mass-to-mass stoichiometry? You've got mass of A here, moles of A, convert to moles of B, and mass of B. This is the step chart or the flow chart that you would use to do a mass-to-mass stoichiometry. But what if we are not solving for mass? What if instead we're solving for a volume? And of that volume, it's either a solid or a liquid. Well, we can't just stop at grams here in mass of B. We need to go one more step. And we can use a conversion factor known as density. Because density is measured in grams per milliliter, or you can use it flipped upside down as milliliters per gram if you'd like. And depending on what you want to do with it, you could use the density inverse. And in this case, since we're going to be going from grams to milliliters, we want the grams to be on the bottom and the milliliters to be on top. So we're going to use density in this last step, and we are going to invert it so that the grams is on the bottom and the 1 milliliter is on top. You don't really do anything different besides adding an extra step to your math. You could also use it on the front end. Maybe you have a milliliters of solid or liquid, and you're trying to do a stoichiometry problem. But we're not used to starting with milliliters. Instead, we're used to starting with grams. Well, if you have milliliters to start and you know the density of the substance, you can use the milliliters to convert to grams, and then you can carry out the rest of the stoichiometry problem just like normal. Some things to remember though. It's used when finding the volume of a solid liquid or used when you know the volume of a solid liquid, but this is not used for volume of gases. We actually have a different type of problem that we will use when we're trying to determine or solve for the volume of a gas. But we'll do this later in the year when we talk about an entire chapter known as the gas laws. And so we could do a problem like this one on the bottom. Let's take a look. We start with 3 moles of mercury liquid, and that's going to be our starting number over 1 here on the upper left-hand corner. And we're trying to solve for the volume of the mercury, but there is no one conversion that takes us from moles directly to milliliters or volume. So instead, we've got to go from 3 moles to grams using the molar mass of mercury, and then we need to convert from mass of mercury to milliliters of mercury using the density. Now, this isn't a stoichiometry problem, but it has the elements of a stoichiometry problem. In order for it to be a stoichiometry problem, it needs to be able to convert between 2 different substances, and you need a balanced chemical reaction. I'll do an example of an actual stoichiometry problem on the next slide. But this is just here to show you how you can use density in dimensional analysis to solve for an amount of milliliters, in this case, milliliters of mercury. And in case you're wondering, the answer is 44.4 milliliters of mercury, rounded to 3 significant figures. As promised, I'm going to show you an example where it's a stoichiometry problem, and you know it's a stoichiometry problem because you're going to use a balanced chemical reaction, along with density in order to solve. Now first, we need to balance this chemical reaction. And the way to balance this chemical reaction is put a 2 here, because I need 2 nitrates on the right, because I have 2 nitrates on the left, and go back over to the left side and put a 2 in front of my lithium, and now everything else has a 1 and a 1. So we've got a 1 to 2 to 1 to 2 ratio. Now in this first one, it says you have 43.8 grams of lithium in an excess of mercury 2 nitrate. How many milliliters of mercury can be produced? Assuming, again, the density of mercury is 13.5 grams per milliliter. So we start with the 43.8 grams of lithium here on top over 1, and we use the molar mass of lithium. The molar mass of lithium is 6.94 grams per mole. So I'm going to put the 6.94 on the bottom and the 1 mole of lithium on top. Next, I need the mole to mole ratio, where I'm going to put 2 moles of lithium on the bottom because I need moles of lithium to cancel out from the step from before, and we're converting to moles of mercury, which is a 1, based on the balanced chemical reaction. Next, I'm going to use the molar mass of mercury, which, if you remember from the last slide, was 200.59 grams per mole, and I'm going to put the 200.59 this time on the top with 1 mole on the bottom. And now I need to solve for milliliters of mercury, so I'm going to take it one additional step, and I'm going to use the density. I'm going to put 13.5 grams on the bottom with 1 milliliter on top, and now I've got the work set up, and all I need to do is punch this in my calculator, and the correct answer is 46.9 milliliters of mercury. And I'm going to keep that as 3 significant figures because the only measured value is the original 43.8 grams of lithium from the start of the problem. Now I'm going to leave this last one for you to try as an example in your notes. and work it out. This time you want to start with the milliliters of mercury, so you want to use the density in the first step. And then you're solving for grams of mercury 2 nitrate. You're going to need to figure out the molar mass of the mercury 2 nitrate, and once you do that, that'll be helpful in solving this problem. Now I'm going to shift gears a little bit and talk about how to use concentration, or what we call molarity, in order to do a stoichiometry problem. Now this doesn't add an additional step on the end after mass or before mass, but rather it kind of takes the place of mass in the flowchart of stoichiometry. Now we're still going to have the moles of A and moles of B in the middle, but this time we're going to use the molarity as a way to get to moles or a way to get out of moles. And what is molarity? Well, molarity is a measure of concentration. It's the ratio of solute dissolved into a solvent, typically water, to create a solution. And that is usually measured in moles of solute per liters of solution. Molarity is moles per liter. And it's got 2 units, so it can be used as a conversion factor. So you can use moles of solute over liters of solution in order to basically take a volume of a liquid in an aqueous solution and convert it to moles. Once you've got from liters to moles, then you can do a mole to mole conversion just like you would in a stoichiometry problem. And you could also use a molarity if you had another molarity, a second molarity, to convert from moles to liters of an aqueous solution. So you can see now our flowchart has liters of aqueous solution at the front and liters of aqueous solution at the end, kind of in the place of where those grams were in the last mass-to-mass sort of flowchart that we used before. When you're given molarity, for example, 6 molar HCl, what that means is that the 6 molarity is the same as saying 6 moles of HCl over 1 liter of solution. Or if you need it to be inverted, you can do 1 liter over 6 moles. But anytime you see a capital M in a problem, think moles divided by liters, because that's going to be one of your conversion factors. So we're first going to do a couple of examples of just practice with molarity. So we're not going to introduce the stoichiometry quite yet, but we're going to show how we can use molarity as a conversion factor, just to kind of convert between volume and moles and moles and volume. Now in this first one, you have 325 milliliters of HCl solution, and the concentration is 5.0 mole. Remember, it's 5.0 moles per 1 liter of solution. So what's the mass in grams of HCl solute do you have in the solution? So this is just simply taking the volume, but we move the decimal 3 to the left to convert it to liters. It's 0.325 liters over 1. And now we're going to take that molarity, which is 5.00 moles of HCl in 1 liter. Now that's going to cancel my liters. Now if I stop right here, I'd have moles of HCl. But I want to stop at moles of HCl because I want grams of HCl. So anytime you need to go from moles to grams, you use the molar mass. Well, 1 mole of HCl is equal to 36.46 grams added up off the periodic table. And now I've got my numbers. I got 0.325 times 5 times 36.46, and the answer is 59.2 grams of HCl. We can also do it kind of working in reverse. I have 55.5 grams of HCl, and I want to make a 3.11 molar solution. What volume of the solution do you have in milliliters? Well, just like before, we're going to start with the number we're given, and this time we're going to start with the 55.5 grams of HCl. And this time I want to go from grams of HCl to moles of HCl, and I'm going to use that molar mass, 36.46 here, down on the bottom. This is going to get me to moles of HCl. Now I want to use this molarity, remember, which is equal to 3.11 moles per 1 liter, and I want the 3.11 moles of HCl on the bottom and 1 liter of HCl on top. So grams cancels grams, moles cancels moles, and this time it's going to tell me the volume, liters, that I need, but I need it to be in milliliters. So I'm going to convert it to milliliters after I calculate it. So once I do this, the answer is 0.489 liters, and to convert from liters to milliliters, I'm just moved the decimal point 3 times to the right, and I got 489 milliliters as my final answer, rounded to 3 significant figures. Now I'm going to show you how to use molarity in a stoichiometry problem. We know it's a stoichiometry problem because it's got a balanced chemical reaction. Now we balance this chemical reaction first by putting a 2 out in front of the HCl because I need to double my hydrogen, and everything else is a 1, and so I've got my mole ratios established from the balanced chemical reaction. This time I'm going to start with 1.04 grams of zinc, and it's asking how many milliliters of 6.00 molar HCl do you use in this reaction? So like I did before, I start with my grams of zinc. Now I want to convert from grams of zinc to moles of zinc, so I want moles of zinc on top. I want grams of zinc on bottom. The molar mass of zinc is 65.38, so I'm going to put that in the bottom. Next, I want to use the balanced chemical reaction where I want 1 mole of zinc because of the balanced chemical reaction, it says 1 mole. And I'm converting to HCl, so I need 2 moles of HCl on top. Now, normally I would go from moles of HCl to grams of HCl, but I don't want to do that because I'm looking for milliliters of HCl. So I'm going to use the molarity. Remember, this is 6.00 moles per 1 liter, and I'm going to put the 6.00 moles on the bottom and 1 liter on top. And then I'm going to do one more conversion where 1 liter is equal to 1,000 milliliters. Now you could do this in a conversion step, or you could just solve for liters and then move the decimal point at the end. Either way works for me. So once I calculate this out, I got the final answer of 5.30 milliliters of HCl. Now that's an example where you use the molarity kind of in the latter step, trying to get from moles to liters. How do we use molarity in an initial step? Well, very similar. We start with 4.5 milliliters, and we want to convert that to liters, so we move the decimal point. That's 0.0045 liters over 1. And now I can use the molarity of 6.0, which is, remember, 6.0 moles per 1 liter, and I want to put the 1 liter on the bottom and the 6.00 moles of HCl on top. That converts from liters to moles. Now I'm looking for mass in grams of hydrogen gas. So I'm going to go from moles of HCl here on the bottom to moles of H2 on top. And it's 1 H2 for every 2 HCl's. Moles cancels moles. We have moles of H2. And the last thing I need to do is use a molar mass of H2 to convert to grams of H2, which is 2.02 grams because it's 1.01 plus 1.01. And I get a final answer of 0.027 grams of H2. Now that's only 2 significant figures because my original number, 4.5 milliliters, only included 2 significant figures, so my answer can only have 2 sig figs. And this is an example where you would use molarity in an initial conversion to get to moles and then execute the stoichiometry problem from there. Well, that takes care of this video lesson on how to use density and molarity in stoichiometry practice problems. Thanks for watching.